I like MATLAB answers.
All right. I told you before, with the computer side of it,
Yeah.
my strategy is to isolate the tone so I can isolate the frequency. But I basically end up having to use the wave root function 10 times to isolate it.
Okay. Yeah, that's fine.
But I want to use a loop to simplify it. That way I don't waste a half a page of code.
Okay.
But I keep getting an error that says, you know, A parenthesis I, or A sub I assigned to B, you know, the vector like.
Yeah. Okay.
And I think it's the file, like the file argument of the wave read that's screwing it up.
So you're still accessing the wave read file 10 times. You're just looping it so that you can somehow instruct it.
Yeah, can I just write up on the board?
Yeah, sure. Come on, we'll all learn something. This is good. So there's basically two strategies. I just emailed you back about that, by the way. I mean, okay, good. I mean, there's here. You just want to do this one suck. So there's two basic strategies. One strategy is.
Oh, this one kind of sucks.
To the purple one, the good one right now. Like you can either use the wave read file once, load in the entire file, and then access the samples you want out of the array, or you can use the wave read file 10 times and pass it parameters so that it only loads the samples that you want. Either way is the same thing. I mean, either way is going to get you to the same thing. So, you know, then there's this question of, can you write a loop to automate some of it? And you totally can write a loop to automate some of it, but, you know, for an assignment like this, there's nothing essentially wrong with, you know, like hard coding it in, like just making a big old file. Okay, so let's see what we've got here.
This is based on just I'll have a little bit of, you know, be for t assigned to 1.
I know exactly what the problem is.
And I feel like it's this right here.
Nope. It's not that. Okay, your problem, well, you may have many problems, but you walk into that one. Okay, well, so a couple thoughts. So, I'm guessing what you've done is you've already gone ahead and created an array of 10 start elements and an array of 10 end elements where you actually go and tell it, like which sample, you know, start of 1 should tell the file what sample number. Yeah, so you've already done that.
I have that in the same loop, basically, you know, a start is assigned to this, and that works out just fine.
Okay, so one thing right off the bat that's going to cause you problems. You can't use end as a variable name.
It's actually end position.
Okay, just don't try that. MATLAB will barf on you and you won't know why. End is a reserved word. You can't use that.
Yeah,
it needs end for other stuff. Okay. There's another common, along that thought, this is a bit of an aside, but another common mistake that people make, when they go to name their MATLAB file, their M files, people will be like, they'll be doing a homework assignment. They'll be doing, you know, question number 1. So they'll call their file 1.m. It will not work, and you will not know why. Basically, when you do this, like if you have a file and you call it, you know, like hello.m, then if you go to the command line and type hello, it will execute that file. It associates the word hello with running that file. So if you now go call your file 1.m, and you type, and from now on, if you type in 1, it gets confused. Are you talking about the number 1 or the file 1? Right, and then it doesn't produce an error, I don't think. It'll just run this file when you mean 1, and you get all sorts of crazy errors. So, and it's impossible to debug because you're looking in the code for a mistake, and there's no mistake in the code. The mistake's in the file name. Anyway, I don't know why that just randomly popped into my head. Okay, so the reason you're getting an error is the following. When you say tone of t, what you're telling MATLAB is that I'm going to get a tone, so this is going to read in some number of samples. And I'm guessing for each pass through the loop, it's going to be a different number of samples depending on the values of start and end that you've picked, which is fine. When you express tone of t like that, essentially what you're telling MATLAB is, I want to have an array called tone, and I want the t element number t of that array to be a number, right? It's imagining, in MATLAB's mind, it's imagining that there's going to be an array called tone with 10 elements. Okay, and you're basically saying, I want, so let's say this comes out to 1,000 samples. So what MATLAB thinks you're trying to do is you're trying to cram all 1,000 samples into tone of 1. And that's why it's complaining at you. It's saying you can't take 1,000 samples and assign it into one element. So that's the problem. So there are two solutions. Either one is fine. Solution number one is just to ditch the parentheses t. So in this case, what you're doing is you're saying, load in these samples, however many it is, 1,000, 2,000, I don't care, and assign that string of samples into tone. All right. Then, still within the loop, right, because your loop's going to have a whole bunch of lines in it, then still within the loop, you're going to run your analysis. Analyze
Oh, I already got
tone.
it. I can say that tone is assigned to put that in an array. Oh, no, never mind.
No, that won't solve your problem. Yeah, if you do it, then essentially every pass through the loop, you're reassigning the value of tone. You're recycling it. Okay? But then you'll just have to do your analysis in the loop. So load in the first tone, analyze it, and that's it. Once you've analyzed it, you don't need it anymore. Loop back, load in the second tone, analyze that. Wash, rinse, repeat. Right? Once you've analyzed it, you don't need to hold on to it anymore. That's one way of doing it. There's another way, if you care to know. Almost exactly the same thing that you did before, but instead of saying tone parentheses 1, you say tone curly braces 1. Okay? And that's called, or not 1, t. Okay? And the curly braces produce something called a cell array. And cell arrays are pretty sweet in terms of MATLAB making your life easy. When you have a regular array, right, let's say you have an array X, okay, and let's say X has 10 elements. Okay, the only thing you can stick in X is a number. Okay, so X of 1 is a number. X of 2 is a number. When you define a cell array, X of 1 could be anything you want. X of 1 could be an array of 1,000 elements. X of 2 could be an array of 10 elements. X of 3 could be an image. X of 4 could be, a string. It just doesn't care. It lets you just cram in whatever you want. It's pretty nice. So, what's that? A structure?
Yes,
It's different than a structure. It's different than a structure in an important way. In C, when you define a structure, I mean, MATLAB has structures too. I want to make sure I differentiate between the two of them. It's a good point that you raise. So in C, when you define a structure, you're basically saying, okay, I'm defining a structure, and the structure is going to have, well, it's similar to a structure. It's not totally different. Okay, so you can say there's going to be like a string and a number and a whatever. Okay, and then you can basically refer to like x dot string and x dot number and so on, and everyone's happy. The difference with a cell array is that in a struct you have to preassign. You basically have to predefine the structure, and then once you predefine the structure, you're kind of stuck with it. With a cell array, it doesn't care. You can just reassign it on the fly, right? If you have x of 1 being 1,000 numbers, if for some reason in your code that doesn't work for you anymore, you can just say, hey, x of 1 equals whatever, another string. Okay, you can just reassign it and it doesn't care. So over here, you're sort of restricted by the structure. Like once you define the structure, you can't really deviate from it. Whereas over here, it's like an array of whatever you want. And you can reassign it on the fly as many times as you want. It just doesn't care. So if you do that here, then you could just say tone of t, tone of curly braces t. And then tone of curly braces 1 could be 1,000 elements, and tone of curly braces 2 could be 500 elements, whatever you want. And that's it. Then that would be fine. But then you need another loop to do your analysis. And so then you would just call it out, you just use tone of t. Yes?
So does that iterate the wave read for each
Yeah.
member of the cell array?
Yeah.
Okay.
Yeah. That should work fine.
All right.
That should totally work. Yeah, it's cool stuff, right? It works. Again, though, you have to know when your thing starts and ends. Once you do that, then you're off to the races. Yeah, that was a good question. I like that. Bless you. Is everyone having some luck with the assignment? Mostly figured out the phone number? Yeah, all right. I can tell by those smiles. I thought about making it a number that you should dial, and there'd be like a message there saying like you got it right.
Yeah,
But
somebody said we should get like a bad old professor and like take their number and then throw it in the assignment.
yeah, just crank call them. Yeah, I'm down with that. All right, we good? Okay. Let's see. What's next? Oh, good.
I do have a question about
yes.
start and how are you going to define what start 1 is? Are you going to have to, if you start at equals 1, I've got it broken up into different sections of the data that I'm going to read, but I don't know how you assign one time.
Like how you assign it or how you actually find out what the number is?
How do you assign it?
Oh, that's just, you just say, you would say something like start equals square brackets, and then you just list your numbers. Like, so the 100th sample, the 517th sample, the, 1028th sample, and so on, ... If it makes you feel better, you can put commas in there, whatever, and then that's it. If you're really cool, I don't expect anyone to do this.
I took the size and I divided by 10. Yeah, that's what I did. And assumed it was 1 second interval.
But it's not 1 second intervals.
But then I just it worked out, but it was just kind of a lucky.
It is a very lucky assumption. Seriously, that's...
If it didn't match up, I would divide by 9.
Right, but still, the assumption that I've gone out of my way to dial the phone at some regular interval is a big assumption, right? What if I go and give you a new file?
I thought about it, so then I would just if it didn't work, I would change the divider by another number. At first I divided by 30.
Right.
And I thought it was too small by 30.
So there's a lot of ways, so segmenting, so this is actually like an interesting signal processing problem. How do you segment the code? There's actually a lot of cases, there's a lot of applications where you would need to think about how to segment your data so that you could analyze each segment accordingly, right? And obviously, this is a trivial thing. There's only 10 things that you're trying to isolate. But can you imagine, like for example, people that do speech processing, if you want to take a speech file and translate each word, first thing you got to do is find each word. Okay, well, if I give you an hour of speech data, it's going to be awfully inefficient if you have to have somebody who's going to go through that file and manually isolate where each word starts and stops. So there's like a whole science around writing code to just tell when things start, to segment your data. Yes?
So whenever you start dialing a number, the thing goes up.
Ah.
An interval.
Yes.
So I just catch it up, and since it's a frequency, I can't necessarily infer that I'm going to be able to go along and catch it. So I just add a chunk, and then found a chunk I could add that would still end up with 10 coming out.
Okay. Yeah, that'll work. No, that's a strategy for automating it. So like for example, in this case, what you could do is you could apply a threshold, right? And then you could say, you could basically figure out where the signal crosses the threshold, and that would tell you when each tone starts. You could figure each tone lasts for, a quarter second or something. And you could, I'm not expecting you to do this, but I'm saying that you could at least envision a strategy where you write some code that could automatically generate the start, the start and the end array, and then you could just find all the stuff automatically, right? So again, there's a whole science behind that. Just segmenting your data.
So anytime there's an impulse, you almost have an if statement and just say.
Yeah, like.
Sometimes you just click it. Sometimes you will catch the click of not the number, but the key.
Right.
The frequency emitted by.
Yeah, I mean, let's look at. No, that's exactly right. Let me look at. Well, if we're gonna do this, let's do this. Let's actually look at the thing. Where is my command window?
Well, when you dial a phone number, does the phone turn the microphone off?
I have no idea.
Okay.
Actually, I'm pretty sure if you took a reasonably well-recorded, like if you took my tone and played it into a phone, there's a chance it might actually dial the phone for you.
Probably will.
Yeah.
Can we try that?
Yeah, go nuts.
Can we use that phone?
Suddenly, dude. You have tenure yet?
Yeah.
It just got real.
Just got real. All right, hold on. Okay. If you're going to blow a lecture, you're going to might as well blow a lecture, right? This is fun. I mean, sure, I had stuff I was going to talk about, but, this is way more entertaining than looking at another. Okay, what is it? Is it loaded? Oh, I'm the one that's, okay. All right, let's see here. Let's see. Clear. So we are going to say whose, ls. Good. X comma fs equals.
So I have a random question.
Yes,
You
sir.
talked about speech processing,
Yes, sir.
but if someone has a different, you could talk like a different tone, right?
Okay.
Would it still catch that different tone?
How do you mean?
I'm not sure, but like I have, like, I mean, like some people talk with like a squeaky voice. There's a
Oh,
range.
yeah. I mean, that's like a whole layer of speech processing is what to do with different accents, different voices. Some speech recognition systems, like if you've got a British accent, it just doesn't know what to do. That's
Can't play music over the phone 'cause it's not meant for that range.
right. Well, phones have a very narrow frequency band of tones that they transmit. Okay, so hold on. So let's see if this is going to work. So sound scale X comma fs. All right, so let's see. Okay. All right, so we got a dial tone. So what do you think? I should just hold it up to the air?
Bring the laptop closer.
Bring the laptop
Well,
close.
it's coming out of
Right now, I've got it coming out of the speakers. Maybe I'll just.
Hold it there then.
Well, okay, hold on.
The tallest person in
Let's try it both ways. Let's try it one way with just the thing held up to the.
Well, you do have headphones. You can put the headphones right next to the mic. You're wearing headphones, aren't you?
Oh yeah.
Yeah, but they're not. They're just hooked up to the thing that's recording the lecture.
Yeah, but you can plug it in that.
the system you don't want to mess with.
All right, hold on. Let's just try this. It did the beep 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 thing, but that you get when the phone hasn't been dialed.
I mean, I would guess that it doesn't have a microphone, that it doesn't really. I think it would take the frequencies that are emitting electronically, not.
I think you got to get it. The problem is you got to get it into the phone line directly. It might have some kind of a thing that blocks dial tones when you have the microphone on.
Oh, yeah. I bet if I kill the dial tone, then maybe it would work.
As if it's a Bluetooth.
Nah, the phone did the beep 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 thing.
It's probably only programmed to get the dial tones from the generator inside of it.
Right. If somebody could figure that out and let me know, I would be totally pumped.
So then that would be an acoustic. That will work acoustically.
Yeah, I don't know. I don't want to talk about stuff I don't really know. I mean, at this point, I'm just guessing. And okay, let me.
What does the regular phone use? 2 or 4?
2.
2.
Okay. So if you want to talk about segmentation, I mean, here's your dial tone, right? Here's your phone number plotted. you could easily put a threshold, right? You say threshold equals 0.2. Then you could say find everywhere where the signal crosses 0.2. Okay, and everywhere the signal crosses 0.2, that's a phone number. So I could very easily write myself a script that could go and isolate the times when the phone rings. That's not hard to do. So in this case, it's pretty clean because your signal-to-noise ratio is big. It's easy to tell the dialed tones from the quiet segments in between. So you know that could be like a whole other layer of this, is figuring out how to divide out the sounds.
Would you just send it when it's 0.2? And just say,
You would have to know what a reasonable threshold is. Although you could also write code that would estimate what a reasonable threshold is. I mean, I've done that too. Like it never ends. But having some method of automating this is valuable.
Set up an automated prank call system.
Yes. 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 If you've learned nothing else in this class, an automated prank call system. Okay. What telemarketers do? I don't think so. I mean, I think with telemarketers, they just got a computer that dials the phone for you, right?
It does this in
Yeah.
reverse.
Yeah, it does it in reverse, basically. Like, they just sit there with a headset, and the computer just dials the next phone number for them, and they start talking. I don't even think you have to punch the numbers, right? I think that you just sit in front of a screen, and the next caller comes up and cusses at you, and then, you know, I'm eating dinner. Okay. All right, I do want to talk. I've got two things I want to cover today. And one is I just wanted to finish the phase conversation that we had before. And then I want to look at derivatives. Because you did look at derivatives a little bit in recitation this week. So you kind of got ahead of me a bit, which is cool. So I want to go back to the plot that we were looking at in class of, let's see here. I think this is the one we were doing. Remember this? Okay, so what's going on with my phase plot? Right, we understand the magnitude plot made sense. But then we looked at the phase plot, and the phase plot was a headache, and nobody really understood what was going on with it because it was all gibberishy. So let me zoom in a little bit on the phase plot. So let's see, xlim minus 1 to 1. What's up with that? Does that look maybe even a little bit familiar? Yeah, didn't we talk about if you take your rectangular pulse and you shift it, that's going to introduce a linear phase? And then the linear phase is going to get chopped up because MATLAB is going to basically force it to be between minus pi over 2 and pi over 2. Well, that's basically what you're looking at, right? You've got linear phase, but then MATLAB is sort of enforcing that phase to be, actually it's enforcing it to be between minus pi and pi, right? Look at this number down here. Does that look like it's maybe a shade more than negative 3? Okay, there's your negative pi. And this number is a shade more than positive 3. So that's your positive pi. So basically you've got a linear phase. Okay?
why are we getting that little
The little jiggity thing there? That is, I think it's a 0, and that is probably just some artifact of MATLAB's in math. I'm not really sure. Yes?
But the original equation is it's a square with that not been moved.
Oh, somebody asked the hard question. Yes! The original signal is a signal that hasn't been moved. And we argued in class that you should only see the linear phase once the signal has been moved.
It's not expanded.
So why are we seeing linear phase when our signal hasn't been moved?
Might be an artifact of the FFT function.
Sort of.
The intervals are too small.
Nope. This is a fun question. I'm hearing myself echo. Is this microphone on? Sweet. Let's turn that away. Oh, I think it's because I turned the... There we go. There we go. All right. When we did the plot, remember we did the plot on the board by hand, and I argued that when your signal is not shifted, your phases should only be 0 or pi or negative pi. But now we're getting something that's not that case. We're getting a phase angle that's only consistent with with the shifted signal. Okay? But we didn't shift the signal. Or did we?
Is it shifted implicitly somehow in the FFT?
Is it shifted implicitly in the FFT? So here's a question for you.
Oh.
Here's a question for you. Direct your attention to that line where I create my time. You see t equals minus 10 to 10? Okay, so that's how I got the x-axis where I plotted my signal. All right? Okay, so that's fine. That's how I made my plot. But now look at the FFT command. All I pass to it is x. Okay? Now, as far as the FFT command is concerned, it doesn't know where time starts on my plot. I mean, on my plot, I made it so that time started at negative 10 and went to 10. But I could have just as easily plotted it going from 0 to 20. Right? And the FFT function doesn't know. All I do is I pass x. Right? X is just a bunch of samples. 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0. Okay? Separate from that was the array that I created with the time vector. Right? The time vector I created was negative 10 to 10, but I could have just as easily made it 0 to 20. Okay? And that wouldn't have changed the array x. X would have still been 0, 0, 0, 1, 1, 1, 0, 0, 0. So as far as MATLAB is concerned, okay, implicitly, as far as MATLAB is concerned, I am taking a bunch of numbers, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, and I'm saying, give me that FFT. Okay? We're the ones who in our own heads said, this guy corresponds to t equals negative 10, this guy corresponds to t equals 0, and this guy corresponds to t equals positive 10. That was in our own heads. Okay? But when we took this signal and passed it to the FFT function, we didn't give it any of this time information. We just passed it the signal information. So how's MATLAB supposed to know that it's centered at 0? Is it common sense? It doesn't know. So the way the FFT function works, it's literally just an algorithm for number crunching. Okay? The FFT function sort of always assumes that the first sample is at time 0. You with me? The FFT assumes, even though we've plotted the first sample with time equals negative 10, that was just, we made that. The algorithm assumes that the first sample is at time 0. Okay, so if the FFT function assumes that the first sample is at time 0, then in reality what we're taking the Fourier transform of is this signal. T equals 0, t equals 20. Is that a shifted square wave? Yes. How much have we shifted it to the right by? 10. So what we're really doing is shifting it to the right by 10 seconds. Which means in our phase, we should be introducing a phase of e to the minus j omega 10. So our phase angle is going to be minus 10 omega. A line with a slope of negative 10. Is that what we got? Do we have a slope of negative 10? It's negative. That is negative, and I like that. Can we show that our slope is negative 10?
It looks like it goes from pi to 4.
Why don't we zoom in and just try to measure it? Let's see here. Oh, come back. Okay. Let's put a grid on there. Okay, let's get a couple of data points going. So there's one. Oh, actually, I don't even need the data points. I can just read this right off of there, right? Look. Oops. Don't get angry with me. Delete all data tips. Okay, look. it's going from pi to minus pi over a duration of 0.1 seconds. Who said seconds? I'll jump right into those seats. Hertz. Seriously, I want to make sure we can make this work out, okay? So it went from positive pi to negative pi. So it went a total distance of minus 2 pi radians in a duration of, right, so the delta y is 2 pi, minus 2 pi rather. The delta x is minus 0.05 to 0.05. That is 0.1 hertz. So that's radians per 0.1 hertz. Is that right? Right. So this thing is telling me to expect a slope of minus 10 radians per radian. Right. This is telling me to expect a slope of minus 10 radians per second. Okay. So here I got minus 2 pi radians per hertz. Can I convert that hertz into radians per second? How do I do that? If I take this number and multiply it by 2 pi, that will give me my denominator in radians per second. So if I take minus 2 pi rads, so that 0.1 is going to be 0.1 times 2 pi rads per second. So the 2 pi's cancel. Oh my God, you're not going to believe this. What am I left with? Minus 10 rads every radian per second. Okay, so this is what I measured. I measured minus 10, and that was exactly what I expected. So it worked out. Okay, so all you need to take away from this, so what you're going to find is we're not going to spend a ton of time twiddling our thumbs over phase angles in this semester. It's mostly going to be valuable once you get to controls. I just need you to understand that it's there. It's critical in that you cannot rebuild a signal if you only have the magnitude data. The phase angle data is there, and it's, you can't just sweep it under the rug. However, for the purposes of this course, there's not a whole lot we're going to learn. Like, in terms of intuition, you're going to look at the magnitude plot, and that's going to tell you a lot. It's going to tell you which frequencies have a lot of energy, which frequencies don't have a lot of energy. Conversely, you're going to look at the phase angle plot, and it's not really going to tell you a ton. Okay? I mean, in this case, you can see there's a nice linear phase shift, which is like roughly what we expect. But I don't really anticipate that you're going to be looking at these plots and making some sort of like useful connections the way that you would looking at a magnitude plot. But I need you to understand that they're there. And I do need you to at least understand at some level what you're looking at. Okay? And in this case, that's what you're looking at is a time shifted rectangular pulse. Okay? And the frequencies all line up exactly the way you would expect them to. Okay? What happens if I, we discussed what happens if I made my rectangle very small, didn't we? Mm-hmm. If I make my rectangular pulse really skinny, what happens to my sync pulse? It gets really broad, right? And that made sense. So we argued that an impulse with respect to time, if you look at an impulse, the frequency content of an impulse, you had a constant in frequency, which we interpreted to mean that an impulse in time is really a constant, like it has all frequencies. What if we go the other direction? What if we make our impulse really, really wide? What happens to our, what if we make our rectangle really, really wide? What happens to our sync function? Becomes an impulse. It gets really, really skinny. We've seen that before, haven't we? What does that mean? Yeah, if I take my square pulse and make it infinitely wide, what does it basically become? A constant, right? And we've already learned, what is the frequency of a constant? It's an impulse at zero, right? We learned that before when we looked at periodic signals. That was our DC offset, or A sub 0. right? If x of t is a constant, like the constant 4, that's really 4 cosine 0t, right? Because cosine of 0 is 0. So when I say 4, what you've already learned to think about it is it's got frequency at omega equals 0, and that's it. And that's consistent with, I'm just pointing out that that's consistent with our analysis of this square pulse. If you take that square pulse and make it really wide, your sinc function becomes infinitely small, and then it turns into this. So this is really like an impulse. This is really like a sinc function that's so infinitely skinny that it's only got energy at one frequency, omega equals 0. Yes, sir.
You had there that phase is so minus 10.
Yeah.
Omega, right?
Yeah.
So when the area is, so in previous lectures you said omega is minus a, phase is minus a omega.
Yeah.
Why is it minus a omega? Why is it not a omega, not minus a omega?
That's just the way the formula worked out. We derived it. Like if you take a signal and shift it to the right by t units, then your phase angle gets changed by a slope of minus t omega. That's just how the function works.
Because it's not centered at 0 anymore, right?
Right.
Because it's shifted.
Right. So when you apply a time shift, when you shift it in time, you introduce a linear phase. And that linear phase, the slope of that phase, is always proportional to the amount that you shifted it by. If you shift it to the right, you introduce a negative slope. If you shift it to the left, you introduce a positive slope. Pretty tasty, huh? Okay. So we've got square pulses. So I think we're done with the screen for now. So we've got square pulses that we know give us a Fourier transform that's a sinc function. We've argued if you take that square pulse and make it infinitely skinny, then in the frequency domain you wind up with a constant, your energy is constant over all frequencies. Conversely, we've said if you take your square pulse and you make it infinitely wide, then your sinc function gets infinitely skinny, and you've basically just proved that the energy of a constant is just an impulse at omega equals 0. All right? A constant is, by definition, a cosine of frequency 0. So that's a bunch of pieces of that puzzle. I need to introduce one more property now of the Fourier transform before we can move on to substantially more useful things. Okay? We're sort of right at the cusp now where we're done learning the building blocks, and now we can actually start doing some signal analysis. So I just need to finish this one piece, and then we're good to go. So, suppose you have some signal x of t equals cosine omega t. Okay? So, some generic cosine. So now I want to take the derivative of x of t. All right? So can someone help me take the derivative of cosine omega t? Oh. Negative omega sine omega t. Look at you guys with your big calculus brains. All right. Can someone help me express? So yeah, derivative of cosine is negative sine. Then you got to apply the chain rule. The omega comes out. That's awesome. Now, can someone help me express this as a cosine? Negative, hold on. What? See, you guys thought you were smart. I need to make sure we express this negative sign as a cosine. I don't know. Don't guess.
Negative phase.
Are you sure about that? Plus pi over 2? I don't want guessing. I need you to be like, I need you to stomp your foot down and tell me with authority. Damn it, I know the answer.
It's minus.
I don't want a minus out front. How about that? I'm going to insist that there's no minus out front.
since you have the sign right there, make that negative inside. That negative that's outside, put it inside.
Okay, what does that do for me?
So then you have a positive sign. So then all you have to do is do a minus pi over 2, and that will give you a cosine.
You guys are making me dizzy.
That will be, dude, it's just omega cosine omega t plus pi.
Okay, can we all agree that that's negative sign?
Yes.
We all agree that that's negative sign. Okay, so, and can we all agree that this is cosine? That's positive cosine. So what do I need to do to my positive cosine to make it into negative sign? I need to shift it to which direction? To the left. By how much? Pi over 2. So do you think it's possible that this would be the same as omega cosine omega t plus pi over 2? Yes, I think we can all agree on that. Okay, good. Okay, and could I possibly express this as, remember we've been expressing everything as complex exponentials, right? So that cosine omega t is really e to the j omega t. So maybe I could express this as omega e to the j pi over 2 times e to the j omega t. Could I do that? There's also the e to the minus j omega t, right? But let's not lose sleep over that. And what is e to the j pi over 2? That is just j. Okay, so I'm going to do this little derivation. This is it now. We were done with it. J omega e to the j omega t. So essentially, we started with a cosine, e to the j omega t. I took its derivative. What did I get? J omega times e to the j omega t. So this is one of these badass properties of the Fourier transform. Same property exists for the Laplace transform, and it's basically one of the reasons we use it. If you've got some signal x of t that has a Fourier transform x of omega, then if you take the derivative of x of t, you don't need to recompute x of omega. All you need to do is take your original x of omega and multiply it by j omega. Multiplying it by j omega in the frequency space is equivalent to taking its derivative in the time domain. I'll show you a concrete example momentarily. What about the other way? If I integrate x of t, what do you think I do to x of omega? Divide by 1 over j omega. Put your seatbelts on. Got 6 minutes. I think this is in the book too, so if we need to close ranks on this on Monday, we can do that. Okay. Rectangle pulse. We all made friends with the rectangle pulse, right? Minus a, 1 over 2a. We already know what the Fourier transform of this is. But I'm trying to do it another way now to demonstrate the value of what we've just learned. Can someone help me take the derivative of this function with respect to time?
1 over 2a.
What's that?
1 over 2a. It's going from
Impulse at minus a, and then a negative.
Okay, what about here? What's the derivative for all these times? 0. And these times?
0.
And these times? So if we take the derivative of this, it's 0 almost everywhere, except for right there. So let's draw the derivative. So this is x prime with respect to t. So you're telling me it's 0 everywhere except for right there. So right here, what am I going to draw? Impulse. How big is that impulse? What is the area of that impulse? Is it area of 1? It's actually an area of 1 over 2a. I'll let it slide. Let's not fret too much about how I knew that it was. You went up by 1 over 2a. Like if I went up by 1, that impulse would have had an area of 1. Okay, now my derivative, and this happens at minus a. Okay, derivative is 0. So the only other place where my derivative is non-zero is at a. So what am I going to draw at a?
Negative.
It's a negative impulse because here my slope is positive. So you know it had to be a positive impulse. Here my slope is negative. So it's got to be a negative impulse, but also with an area of 1 over 2a. So can you live with it if I tell you that that drawing on the right is the derivative of the drawing on the left?
Can you explain that again? Why shouldn't this be positive, negative slope and positive slope?
Does this have a positive slope or a negative slope? Right here. Is this a positive slope? Right, it's going from a low value to a high value. So it's got a positive slope, but that slope is so positive, it's an infinity. Okay, so that's you have a positive impulse. Whereas here you have a negative slope, except it's so negative that it's negative infinity. Now, can we take the Fourier transform of this by inspection? Watch. Let's start with this impulse. What is the Fourier transform of an impulse?
Constant.
Fourier transform of an impulse, we learned, is a constant. If the impulse has area 1, the constant is a value 1. Now, this is an impulse whose area is 1 over 2a. So if I take the Fourier transform of that guy, it's going to, we'll deal with the shift in a second. But if I take the Fourier transform of this impulse, I'm going to get the constant 1 over 2a. If I had an impulse located at omega equals 0 with area 1, its Fourier transform will be the constant 1. But now what I've got is a Fourier transform not whose area is 1, but whose area is 1 over 2a. Okay, so that just gives me the constant 1 over 2a. And now my impulse isn't located at omega t equals 0. It's been shifted to the left by a units. So how do I account for the fact that it's been shifted to the left by a units? E to the j omega a. So by inspection, this is the Fourier transform of that impulse. Now I got to do the Fourier transform of that impulse. Can someone help me out there? Minus 1 over 2a, that's the area of the impulse, e to the negative j omega a. So look how cool that is. I took a problem that was complicated, and I made it simpler by taking its derivative. The derivative I can get the Fourier transform of by inspection, because it's just impulses. And I know how to get the Fourier transform of an impulse is a constant, right? You can't get a gift bigger than that.
But that's the Fourier transform of the derivative, right?
This is the Fourier transform of x prime of t, the derivative. But I wanted the Fourier transform of x of t. So what do I need to do?
Gotta divide it by j omega.
You have to integrate.
I wish to get the Fourier transform of the integral of this function. That's what I wanted to get originally. So if I know the Fourier transform of x prime of t, if I wish to integrate x prime of t to get my signal back, then what I really need to do is to take this signal, and all I got to do is divide by j omega. That will effectively give me the Fourier transform of the integral of x prime of t. That's what I started with. Okay, let's clean this up a little bit. I factor out a 1 over 2a. What's going on in my numerator? My numerator is what? 2j sine of a omega over j omega. The 2's cancel. The j's cancel. And what am I left with? Sine of a omega over A omega, which is what we got, the same answer that we got when we actually took the Fourier transform integral of the square pulse. Now, if that's not a shortcut, I don't know what is. Because now, so let me just leave you with this thought. I'm out of time, but let me leave you with this thought. Suppose your jerk instructor came to you on an exam and gave you this gave you this function and said, find its Fourier transform. Okay? What would you do? Well, as of 9 a.m. this morning, you would have done one Fourier transform integral for that line, one Fourier transform for this line, and filled about 3 pages with calculus. And cursed me every step of the way, as would be your right. Okay? But now, you look at this and you say, well, hey, this is too hard. I'm going to do the Fourier transform, an easier problem. I'm going to take its derivative. If you take its derivative the first time, you get, this is a positive constant, and then you've got, well, this one's a little bit complicated. Then you've got an impulse here, and then you get another positive constant. Okay? You get that. Okay? This is easier. You can take the Fourier transform of this, and then once you know the Fourier transform, you divide it by j omega, and you got the answer. And if you're careful, you'll always get the right answer. Yes?
Could we do the top two squares as one square?
Yeah, absolutely.
And then could we just add the impulse to Fourier transform?
Well, it doesn't matter how you put it together. As long as you don't violate any laws of calculus or any laws of breaking it apart, you can totally make it work. Yes?
So both those slopes on that triangle one are positive?
Right. These are both positive slopes, but here there's a discontinuity, and that if you take the derivative of that discontinuity, you get a negative impulse. Yes, sir?
So we could also take a second derivative and
Yes!
3 impulses and then
Well-
divide by j omega squared.
Well, okay, in this case, the second derivative, you have to be a little careful because you can't take the derivative of an impulse. It gets messy. So what I would do in this case is I would break this up into the impulse and the rectangle. The impulse, you can just get that Fourier transform by inspection. But the rectangle, you might say, well, let's take its derivative and get 2 impulses. So then what I would do is, I've got this guy, get its Fourier transform, integrate it twice. Then this guy, I can get its Fourier transform by inspection, integrate it once, and add the whole mess together, and you'll be good to go. I love it too, right? No calculus. All right, go away. What? What?